In this video, I will show you an example of load line analysis. This is example 1. I will show you total 3 examples of diode load line analysis. Determine the diode load line, operating point and the current through the diode for the following circuit. See, for this given circuit, I have to draw the load line, find out the operating point, and I have to calculate the current through this diode. And we have to use the provided IV characteristics graph. See, this is the IV characteristics curve of the diode. So I have to use this IV characteristics graph. So what is load line? Load line is the graphical representation of the KVL or Kirchhoff's voltage law in a circuit containing a voltage source, a resistor and a non-linear element. See, this circuit contains a voltage source of 5 volt in series with a resistance of 125 ohm and a non-linear element, a diode, in this loop. So I can draw the diode load line from this given circuit. After drawing the diode load line, the load line of the diode and the IV curve will intersect at a point. That point will be the operating point of this diode. After finding the coordinate of the operating point, I can calculate the current through the diode for this given circuit. Now, to draw the load line, I have to apply KVL in the circuit. From that KVL equation, I will deduce an equation of straight line. Now I will apply KVL in the circuit. Before applying KVL, let me indicate the polarities of the elements. See, this is our diode. Positive terminal of the source is connected with the P side of this diode. So let's say this terminal is positive and this negative terminal is connected here. So this terminal is negative. Let's say the voltage that is dropped across the diode is voltage VD. See, this is the positive terminal of the source and this is the negative terminal. So current will flow from the positive towards this negative terminal. So I will get the current as indicated direction in this circuit. Okay, so let's say the current that is flowing through this circuit is ID. As this is a total series circuit, this ID will flow all over the circuit. Now I will apply KVL in this loop to draw the diode load line. If I apply KVL, I will get plus 5 minus ID into 125 minus VD will be equal to 0. From which I can write ID into 125 equal to minus VD plus 5, from which I can write ID equal to minus VD divided by 125 plus 5 divided by 125. If I further simplify this, I will get ID equal to minus VD divided by 125 plus 1 by 25. Let's say this is our equation number 1. If I compare this equation number 1 with an equation of straight line y equal to mx plus c, here you will see the y will be equal to ID. That means in the y-axis I will take the diode current. X will be equal to VD and the slope of the equation will be minus 1 by 125. See, the slope of the load line is negative. If the slope of a straight line is positive, it will take this shape, but here the slope is negative, so I can expect that it will take a shape like this. And here you will see the y-intercept equal to 1 by 25. So I can say that this equation number 1 represents an equation of straight line. So I can draw our diode load line from this equation. Now I will draw diode DC load line from this equation number 1. Diode DC load line is a straight line, and to draw a straight line we need at least 2 points in the graph. So it will be convenient for us if I find the x and y intersects of equation number 1 to draw the load line or the straight line. If I want to find the y intersect of equation number 1, I will set the x coordinate equal to 0, that means VD equal to 0. In that case, you will see our ID will be equal to 1 by 25, which will give us a value of 40 milliampere. So our load line will intersect the y-axis at a point 0, 40 milliampere. Okay. If I want to find the x intersect, I will set y coordinate equal to 0, that means ID equal to 0. If I set ID equal to 0 from the equation number 1, I will get 0 equal to minus VD divided by 125 plus 1 by 25, from which I can write VD divided by 125 equal to 1 by 25, from which I can show that our VD will be equal to 5 volt. So that load line will intersect the x-axis at point 5, 0. This 5 is the 5 volt. So if I locate the x and y intersects, see x intersect is 5 volt 0 and y intersect is 0, 40 milliampere. Okay, so our x intersect will be 5, that means at this point here it has the coordinate 5 volt 0, and our y intersect will be 40, that means a point like this. This will have a coordinate of 0, 40 milliampere. See, I have total 2 points in the graph. If I connect this point and this point in the graph, I will get our DC load line. Now let me do that. See, if I join this point and this point, I will get our diode load line. And here you will see the diode load line will intersect the IV curve at this point, and the intersection of the load line and IV curve will give us operating point or Q point. And here you will see it will have a coordinate of, see, it will be around 2.5 volt and a current of, see, this is 18, 19.5, 21. It intersects the middle, let's say 20 milliampere. So our Q point has a coordinate of 2.5 volt and 20 milliampere. This 2.5 volt is our VDQ, and this 20 milliampere is our IDQ. See, I have drawn the diode load line and find the operating point. Now I have to calculate the current through this diode. Here you will see this positive terminal will be connected with the P side of this diode, and the negative terminal will be connected with the N side of the diode. That means this diode will be in forward bias, and from this IV curve you will see this diode will have a built-in potential of VD equal to 0.75 volt. So if I replace this diode with its equivalent built-in potential, I will get a new circuit. Now let me do that. I am doing this to calculate the current through the diode. Okay, see, after replacing the diode with its equivalent circuit, simplified equivalent circuit, I will I will get this new circuit. Here, to calculate the current through this path or through the diode, I will apply KVL in this loop. If I apply KVL, I will get plus 5 minus ID into 125 minus 0.75 equal to 0, from which I can show ID will be equal to 5 minus 0.75 divided by 125, which will be equal to 34 milliampere. Okay, that's it. Thank you.